Hello everyone and welcome to another Würth Elektronik eiSos webinar. My name is Markus Eberle and I will moderate this webinar today. We are very pleased that you took the time to participate in our webinar. The topic of today's webinar is EMC Shielding 101 Designer's Approach. Our speaker today is Antonio Alcaria, who is working as product manager in the field of EMC shielding and thermal materials at Würth Elektronik eiSos. He will hold today's webinar and also answer your question. As we also take all possible steps against the coronavirus, we are unfortunately not sitting in the same rooms today, but are holding the webinar out of the home office. In case of technical issues or some delay, please take this into account. We will do our best to make a smooth process possible. Before we start the webinar, I would like to point out one thing. You will be muted during the webinar today. This means that you cannot ask us questions via microphone during the webinar. Nevertheless, you have the opportunity to ask us questions during the webinar at any time via the chat function. You will find the chat function in the webinar control panel. That's on the right. The webinar will be about 30 minutes long. The chat questions will then be answered in a question-answer session following the webinar. There are 10 to 15 minutes in addition scheduled for this. If we are unable to answer all your questions within this time, we will answer them via email after the webinar. If you still have any other questions left after the webinar, just email us at eisos-webinar@we-online.com. We will try to answer all questions promptly. At the end of the webinar, you will be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve our webinars. You will also receive the link to the presentation as well as to the recording of the webinar only in the next few weeks. And now I will hand over to our speaker, Antonio, and I wish you an exciting webinar.
So hi, everyone. First of all, thank you, Marcus, for the introduction. I'm Antonio Alcaria, and I'm holding today's webinar. So we will take a look to the agenda. First, we will do a short introduction to what electromagnetic shielding means. Then we will talk about some basics of EMC and shielding. We will try to explain some basic theory, like mainly the basis, not going deep into the theoretical part. Then we will dedicate some time for the explanation of shielding apertures. And finally, we're going to talk about the different solutions we can use from the beginning of our design in order to prevent future EMC problems. The main goal of this webinar is to provide with a basis for every designer so they can start their design and building up their device with taking into account EMC from the beginning. In this way, they are going to avoid future EMC problems and solve a lot of issues. So what does electromagnetic shielding mean? Basically, it means to place a protection or a shield between our device against external noises. It also can mean to protect some parts of our device against different other parts from our device. So for example, for this, RF stages are very sensitive, so it's really common to protect them with the shielding in order to avoid problems coming out for the coupling or interference with the power stages of the design. So as we said, mainly is to place a shield between undesired noise and our device or parts of our device. Every conductive structure that we have in our device or our design can be behaving like an antenna. This means that they can be either radiating noise or picking up noise, even both. What is this meaning? Every conductive part, this means from cables till traces and heat sinks, everything: inductors, transformers, the ground planes, the slits we create between different planes in the PCB, all the interfaces, apertures on the housing. Everything conductive can behave like an antenna. In this slide, we are showing this equation. Please have it in mind. You don't need to take notes because you will receive afterwards the presentation. But this equation relates the wavelength of a signal, of a wave, with its frequency, with the speed of light, of course. So, as we can see in this table, the higher the wavelength is, the lower is the frequency. So the speed of the signal is higher when the wavelength is lower. Here we have some examples about some calculations. For example, for the Wi-Fi frequency, we can see that the wavelength is around 12.5 centimeters. With this equation, it's really useful because we can use it for a rule of the thumb that I will explain afterwards in order to prevent future problems. One of the basics antennas is the electric dipole. This electric dipole is composed by these two parts, and it has a current flow between one side and the other. So the charges are flowing, the current is flowing, and it's changing the sign all the time. This creates an electromagnetic field, and it's able to radiate a signal or to pick up different signals. The length of this electric dipole normally is wavelength, half the wavelength. Electric dipoles are mainly generating electric field. This doesn't mean they don't generate also magnetic field because they are together, but mainly it's electric field. Every conductive structure, we said that it can behave like an antenna. So every conductive structure can behave like a dipole antenna. Does this mean that every conductive structure can be a good antenna for every frequency? No. We can consider that an antenna is not a good antenna. It can be discarded about talking about problems or radiation problems when the wave or the size of this antenna or the size of this conductive part is around 1/20th of the wavelength of the noise. A perfect antenna will be half of the wavelength. 1/20th means a really, really bad antenna. So when we are having problems in our device and we are measuring different noises that are being radiated from our device, we just need to see the frequency of this noise, and then we can calculate with this between half of the wavelength and 1/20th of the wavelength. We can calculate the difference, the different distance using this equation, the different wavelengths that are dangerous from our device. So every part that has that it's in this range could be radiating this noise. So for example, if we are having noises with a really high wavelength, meaning low frequency, most likely we will have radiation coming out of the cables and long parts of our device. It would be cables, housing, and so on. A second elementary antenna is the magnetic dipole, or the magnetic loop, current loop, it has many names. So basically, this antenna is able to radiate magnetic field. So for example, if you remember university classes about the PCB design, there was always a rule about not to create big loops or laces with the traces when tracing the PCB. This is coming directly from here, because when we are creating these big loops, we are turning our traces in a magnetic antenna, a current loop. So this means it's able to radiate part of the energy that is carrying to the outside, and also it's able to pick up signals coming from the outside. So another basic thing is the impedance of a wave. So we can calculate the impedance of any wave by the relation between electric and magnetic fields. So we can measure the electric field and the magnetic field, and with this relation, we can see, or we can calculate the impedance of this wave. How can we divide it? Because normally we have near field and far field. So for the near field, we have these two equations for electric field and magnetic field, which allows to calculate the impedance of the wave. This value here is a factor, so it's a constant that is calculated like this. This is the free space characteristic wave impedance. It can be calculated with the permeability of the air and the permittivity of the air. That's why it's a constant and it's considered like this. And the value is around 377 ohms. So we can consider in the far field, this is the impedance of the wave always. And in the near field, we can calculate it with these two equations. If we take a look from the EMC perspective, most of the relevant noises that are created in our device or coming to our device can be described by one of these two different antennas, either the dipole antenna or the magnetic dipole, depending if the problem is mainly in the near field or electric or in the far field, and also if you are measuring electric field or magnetic field. This is the relation we have between electric field and magnetic field. We can see the magnetic field starts with low values, growing with distance until it's stable. And here we have the 377 wave impedance of the free space. For the electric fields, it is the opposite. This transition distance can be calculated with this equation, this small equation. So when we want to place or to create good shielding, what we need to do is to create a big mismatch between the fields. So if we have, for example, an electric field that they normally have high impedance, what we need to do is to place a shield that has very low impedance. This means that you're reducing the electric field because you are ensuring good conductivity. On the opposite, when you have a magnetic field and you want to provide shielding against it, you need to deal with it like ensuring you have or you place something that has a really high impedance. You can think about it like when you design a PCB, you always want to have a common impedance. So for example, the most common value is 50 ohms or 100 ohms. And you want everything on your device to be balanced and to have this impedance. So what happens if you have a trace and suddenly you place a really big impedance? The signal that is going through this trace is being reflected. So the same happens when you are creating this mismatching for shielding. Why I'm talking about the near field mainly is because it's much easier and cheaper to solve problems in the near field than in the far field. How can we shield against electric fields? This is really easy. For electric fields, we said that we have two parts. This is the dipole, it's exactly the same structure. We have two parts and we have a transfer of power from one to each other, a current flow. And what we need to achieve is to have the charge on both sides balanced. How do we do this? Reducing the impedance that is initially in the middle. Here we have a really high impedance, like we were saying on the table. And by connecting these two parts, ensuring a good connection, we are reducing this electric field nearly to zero. So basically, we are placing really low impedance connections in order to let the electric field go through this part. When shielding magnetic fields, thing gets a bit more complicated. The thing here is that depending on the application, there are different ways of solving it. Even sometimes more than one way can be used in order to solve a problem. Normally, against the low frequency fields, we can use high permeable materials. Against medium frequency fields, we can make use of the skin effect. And then high frequency fields, we can use materials that are able to reflect or absorb this magnetic field. With these materials, many times it's possible also to solve the other two problems. So some examples about high permeable materials are these ones, metallic materials. Mu-metal is the most common one to use in very low frequency noises, these ones. And for any shielding, any kind of shielding, in the case of for magnetic fields, the higher the permeability of this material, the higher the effect. Also, the thicker the material, the higher the effectivity of the shielding. And the same for the relation between the shielded volume and the size of our shielding. We will see some explanations about this with magnetic materials later and some results that we measure. This is a calculation, a graph about calculated attenuation in order to provide a reference. So we have copper and aluminum, and we divided it in reflection and absorption capabilities. So as you can see, we have different behaviors depending on the material. Normally, we define a limit for measuring the shielding effectiveness or the shielding attenuation that is around 120 dBs. Why is this? This is because of the ground floor. It's not possible to measure more. And most of the cases, it's not necessary. A normal shielding or a good shielding is considered around 20 dBs or something. Many times, also to solve problems in the EMC test or previous to the EMC test, it's only necessary to go down like 5 dBs and so. There is no perfect shield. In fact, there is. But what's the thing? That we cannot use it. Why? If you think about any device we have all around us right now, if the perfect thing would be to use a Faraday cage, so to enclose it totally. In this way, we are containing all the noise inside, and we are also preventing that external noises can be coming to our device. That sounds nice. What's the problem? That we need to have some connections. Why do I need a phone if I cannot make calls? I cannot connect it to the headset. I cannot use it to check, to use internet, and so on. Why do I use the Wi-Fi router if I cannot connect any device to it? So we need to have apertures, and we need to have signals coming in and out of our devices, either by cables or by wireless connections. Also, in order to prevent the self-heating of components, we also need ventilation, so it's important to have apertures. What's the thing? That there is a really big impact of apertures in the shield or on the effectivity of the shield when we are creating these apertures. When we are going higher in frequency, these apertures become more critical, because the higher the frequency of the noise is, the easiest they can go through holes and apertures. What's the critical distance we need to have in account when we have apertures? The maximum dimension. So this means always we need to have in account the maximum aperture length. So in this case of the slit is this one, and this case of the square is this one. And with this distance and the equation we were showing before that related the wavelength and the frequency, we can calculate until which frequency this aperture is kind of it's blocking, and when frequencies the signals are able to get through it. So we calculate, like with the dipole antenna, we can take the length close to half the wavelength, and then it shows the same behavior as the dipole antenna that we were showing before. One easy solution in order to prevent this, or in order to, it's not prevent this because you cannot prevent it totally, it only reduces the effect, is to divide this big aperture in small apertures. In this way, we are making worse the behavior of the antenna. We will still have it. And also we need to take into account this distance and this distance, even so. But this antenna, even taking into account this distance, it's much worse, it's much worse than this one. When we have a matrix of holes, like for example for ventilation, that is really common, we are also making worse the attenuation. So when we are doing this, there is a way of calculating how we are diminishing the shielding effectiveness of our enclosure. With this equation, taking into account the number of apertures and the maximum linear length or dimension, we can calculate the attenuation that is created by this matrix of apertures. This n number should be the maximum number of apertures, either in this way, in this direction, or in this direction. As a reference, we can use these two tables. These are very useful. So we are calculating here for 20 dBs of attenuation by different frequencies. For these different frequencies, the maximum length in centimeters in order to achieve at least 20 dBs of attenuation that we said before is considered a good shielding. So when we have, for example, 1 gigahertz, the maximum length for a slit or aperture should be around 1.5 centimeter. If we exceed this length, then we are making worse than this 20 dBs the shielding effectiveness. When we have more than one aperture placed together, the number of these apertures is also affecting the shielding effectiveness. So as we go in increasing the number, shielding effectiveness or the attenuation of the shielding is being worse. So now we're going to talk from these problems with some solutions some products we can use from the market in order to solve these problems. For the first one, apertures in the housing and any kind of apertures, we can talk about displays we need to create, or interfaces, connection for cables, and so on. This one, we said there is an antenna, and this is an antenna. We have a transfer of power from one side to the other. What we need to do is to ensure good connection between these 2 points. What we can do to place these kind of gaskets, these ones. Even if we have, like this, in this case, we have a box that is composed by a cover and an enclosure, we could think that this is a good connection. We have our cover placed perfectly. But if we take a look to it with a microscope, we can see that the surface is not regular, it's not straight. Why? Because it's mechanically impossible to create straight lines or straight structures to make perfect contact. That's why with the using of these gaskets, placing in the middle, they are able to adapt to these differences and to fulfill these slots. Mainly, there are 2 main kinds of gaskets: the conductive fabric gasket and the spin contact. First one, the fabric gaskets, are composed by a foam material on the inside, and they're surrounded by a nickel copper fabric. I say nickel copper because I'm talking about a standard one, but it can be also different materials can be selected such as aluminum, copper, whatever. So this surrounding layer ensures a good connection between the upper part and the bottom part. Here we have an adhesive layer that also sometimes can be conductive, although we are not measuring any difference in the behavior using using a conductive adhesive or not, because when you are compressing this part, these sides are touching the other surface. So either way, we have a good connection between these points and these ones. There are different profiles depending on the final application and the needs of the design. One thing to have in account, that's why I was talking about the materials, is that we need to ensure always a good galvanic compatibility. Why? Because in this way, we're avoiding future corrosion problems. So if we have a housing, for example, made out of aluminum, that is one of the most common ones, we need, or the perfect thing is to use a gasket that has a surrounding layer made out of aluminum. This way, we have a perfect galvanic compatibility. The other kind, the spring contacts, are basically mechanically more resistant, and that's why they are used on doors, for example, for this anechoic chamber that we have in the main labs in Waldenburg. So normally in the using of doors or covers that need to be opened and closed many times, it's recommended the use of this kind of gaskets or spring contact strips, because mechanically they are more robust. A special case that now is being used more and more with time is the elastomer gaskets. These gaskets are made out of an elastomer with embedded particles that are conductive on the inside. So this means that they are basically the same as these ones, but they are with a recommended compression. They are providing the design, and the final device makes this device able to reach until IP68 of protection. So it can be helping your device to be waterproof on the joints. So important thing is that housing does not end just on the enclosure. You need to take in account that when you have a cable, this is an extension of your housing. So you also need to shield the cable and to end it properly on both ways. This is a question I received many times. The cable needs to be ended in a proper way. What does this mean? For example, the using of this kind of clips ensures a 360-degree connection to the ground. That is normally where this shielding of the cable is connected. It's not necessary to use 6 of them like in this picture, 5 of them like in this picture. With one of them is enough. What are we preventing with this? The most common kind of connection that I ever seen in customers when they request advice and so on, or engineers in general, are these kind of connections. We have the shielding of the cable and we directly solder it either to the housing or to the ground of the PCB. When we are doing this, we're creating a problem that is called pigtail. Why? Because when we are going higher in frequency, or there are signals of high frequency going to this shield or to this part, this is behaving like an inductor. And when this is behaving like it's creating a parasitic inductance. This parasitic inductance, it's able to create noise when we're going high in frequency. And this noise goes through all the shield of the cable. So at the end, what we're creating is a really big antenna with our cable. So it's not just that our connection is not good because it's not 360 degrees connection to ground. It's also that we are turning our whole cable in an antenna, able to pick up noise or to radiate this noise generated by this parasitic inductance. On flat wires, it's really common the use of this kind of tapes. So we have the conductive fabric, and we have aluminum tape and copper tape. It's important to know that this shielding, these tapes, needs to be ending or needs to have a proper ending. This meaning that we need to connect them to ground also. If we leave them floating, then we have a big surface that has no connection to ground, and if they are able to pick up noise, they're also able to radiate it. So they can be picking up noise and coupling this noise into the flat wire if we do not ground them on the sides properly. Another solution for these flat wires is the using of magnetic absorbers that we will see later. Now going to the board level shielding, the easiest, most common solution, and one that I recommend should be used from the beginning, is the use of shielding cabinets. These shielding cabinets are behaving, or they behave mainly like a Faraday cage. They are 5-sided, and the 6th side is the ground plane of our PCB. How can we use, or how are they useful for us? These cabinets can help to prevent all the noise coming out of some part of our device. Could be a noisy IC or some noise part like traces and so on. Also, they can help protecting parts that are sensitive. One really good example about this, one thing that where the cabinets are used a lot is in the protection of RF stages. For example, when we have the RF matching, we want our matching to be perfect in order to have a really good radiation pattern and radiation level of our antenna. So any noise that is coming out from the outside to our matching is affecting the impedance of this matching, and then it's changing the behavior of the antenna a bit. Normally, you can put, or the perfect thing is to put one of these cabinets on the matching, and then we are protecting this noise. We are protecting this matching against the external noises. When the noise is coming to the cabinet, it's absorbed by this structure and is redirected straight and directly to ground. They normally come either in one-piece solution or two-piece solution, depending on if optical inspection is necessary or not after soldering. Also, they can be used with SMT clips, but only the one-piece solution, in order to make them pluggable. They can be normally customized with different shapes and internal departments in order to separate different stages of our device. This is really common, for example, in mobile phones, boards for computers, and so on. This product is really useful for prototyping especially. This is basically a nickel silver sheet that shows almost the same behavior as the standard shielding cabinet. What you can do with it is that you can bend it in the way you need it for your prototype, and then either solder it directly or use it in combination with the clips. So you can create your own shielding cabinets when you are doing the prototype. It's a really cheap way of creating the prototype, and then when you are sure and the size you need and where do you need it, then you can check the standard sizes or either request a customized solution. Now we're going to talk about the magnetic shielding. Magnetic shielding can be applied in board level shielding or housing. We will explain here also some specific problems. That's why I didn't take them out of this special section, we will say, because these problems are really specific for these materials. Are not something that can be solved in general with different shielding materials. Here we have an inductor. Here we can see two kinds of problems that can be solved with these materials. We have an inductor that is radiating noise and is affecting other PCB we have together. Let's think about that we have a design with two PCBs. So this inductor has an electromagnetic field that is affecting the other device. When we place these absorber sheets, we are containing this noise in order to prevent it to reach the other PCB. The same way, we have a housing and we have a noisy circuit in our electronics. Part of this noise, we can place one absorber sheet. It doesn't matter where we place it. And every time the noise is going through this absorber sheet, the noise is reduced. So it trends to zero. This materials is composed by a polymer mixed with a metallic powder and magnetic properties. One of the main properties of this material is the permeability. We have two values of permeability, the mu prime and mu2 prime. Mu prime stands for, or we could say that mu prime represents the reflection capability of this material, while mu2 prime represents the absorption ability of this material. So it depends what we want to do with this material. If we want to protect some part or we want to use it on an antenna, we need to take a look to the reflecting or the absorbing part. Here we have some measurements representing also another kind of problems. So in order to solve, for example, radiation coming out of traces or noise that is going through traces, we can place these absorber sheets right on top of these traces. They have an adhesive layer, so we can just stick it. We can measure this behavior by a microstrip line, and then we have one signal coming out of our network analyzer and then going through the microstrip line to the other port. Then we place the material on top and we can see the difference. So we are measuring the absorption ability of this material. Here we have different materials, which means they have different permeability values and the response. Now we have the same material with the same permeability behavior, because permeability doesn't change with the thickness. It's an inherent property of the material, doesn't change with size or thickness or any dimension. And then we have same permeability values, different thicknesses. As you can see, if we need to shield in higher frequencies, so for example higher than 8 GHz, it's recommended the use of thinner materials because they are able to preserve this attenuation effect for higher frequencies. If we need more attenuation, we can use thicker materials. But the attenuation peak is going shifted to lower frequencies. Another magnetic material that is pretty similar to the previous one is the ferrite sheets. These are sintered ferrite sheets. They are flexible. They also have an adhesive layer, so they can be directly stick. And they're mainly used on near-field for near-field shielding, NFC, RFID, and wireless power transfer. Why? Because they have normally it's possible to reach really high permeability values with these parts. With these parts, why do we need high permeability values? Because we can place them directly close to the antenna of our NFC system or our wireless power system. In this way, what we want is to have a really high reflection ability of the material with low absorption, meaning not creating losses in the communication. We want to improve the communication, not to create losses. So for example, this is the frequency for wireless power transfer. This is the frequency for NFC RFID applications. And we need to choose the material that provides really high reflection, having very low losses. How do these materials help in these cases? When we have here an NFC RFID system, we have the transceiver and receiver, and this is a metal plane that is close to it. We can think about it like in your phones. Your phones have NFC connections, and they have the case. This case is most of the cases in metallical, or they have the battery also of the phone can behave like this. So this metallical layer, or this metal part or battery, is able to absorb part of the electric field or the field generated by the transceiver, and it creates eddy currents. This is called eddy currents on the surface of this metallical part. These eddy currents create an opposite field, and this opposite field creates a shift in the communication frequency of the transceiver. When we have a shift in the communication frequency of the transceiver is transmitting a different frequency than expected for the receiver. So we are also totally making worse the communication. And then the receiver is not able to receive the signal that is expected. When we place this material in the middle, we are preventing these electromagnetical fields to reach this layer. And we are also redirecting the part that it was lost, going to the bottom side upwards. So in this case, also we are improving, not only we are protecting the communication against this kind of problems, but also we are improving the communication and the power of the signal. In the case of wireless power transfer, we have here a simulation. These are a transceiver and a receiver. Here, without any kind of shielding, we can see that there is some part of the electromagnetic field that is going out of these two coils. So we are losing this power. When we place these two ferrite sheets on top and bottom, now the antennas are on the inside, these two coils, we are concentrating the electromagnetic field on the inside. We're improving the communication. We are making that the amount of power that is going from the transceiver coil to the receiver coil is higher. And a special case is this one. This is a similar material like the first one with the absorber sheets, but it has some ceramical particles inside embedded for heat conduction. So, for example, in this case, we said that heat sinks can behave like an antenna, because they can create parasitic capacitance in connections through the air with the PCB. When we place this material in the middle, we are preventing this noise to go through the heatsink and to the heatsink, and at the same time, as it has good thermal conductivity, we are letting the heat go through the material to the heatsink in order to be dissipated. Another kind of shielding is the contact springs. These contact springs are very low impedance connections and are used to connect different PCBs, for example, to share the ground plane or to share power planes, also to connect the PCB ground to the housing ground, and so on. It's a special kind of these ones that they have a mechanical protection against overcompression. So mechanically, they cannot be overcompressed. So they have better behavior with time in mechanical terms. These parts, as they are very low impedance connections, they are also used in the connection of signals. So for example, for RF circuits, when we want to connect an antenna module, or as we said, to share a power plane from one PCB to the other, or a signal. This is a mix between a contact finger or these contact springs and a gasket. So basically, you can use it as a contact spring. It can be soldered on the PCB, but mechanically, it is like a gasket. So it's another option you can have in account when using either these components or these components. Finally, we have these grounding strips that can be used in combination with the spacers to connect the ground to the housing. Normally, the tapes are used for the grounding in prototypes, not in final designs. And these are made out of twisted wires on the inside in order to prevent as much as possible the pigtail effect. So we need these long distance connections, and there is no other way than doing it with cables. We can use these twisted wire cables designed in order to avoid pigtail effects. So this is all. I think I didn't went up over the time too much. I hope you all enjoyed, and thank you for listening. Now we will wait for your questions.
So thank you, Antonio, for this really interesting presentation. And as you mentioned, now we'd like to take our attention to your questions, and we wait a little until some questions come in. You can send us your questions via the webinar control panel with the chat function on the right. So we have the first question, Antonio. What is the most common and correct method of applying spring contact strips to the case of the device? Is it a screw, conductive glue, or soldering?
So for the contact strips, normally the most common way of let me show it on the presentation so we can all know what are we talking about. I can reach it. So basically, it's the most common use is with the screws all around, but they also can be used with glue. The problem when we are using it with glue is that the gaskets are really flexible. So when you are compressing it, they can go over this glue in order to make good contact. But for these ones, it's not that easy. So that's why normally they are mechanically fixed with either like clipping the part or with screws. I would say this is the most common way.
Okay, so thank you, Antonio. And let us come to the next question. Why HDMI signals are very sensitive to emissions? Do you have any shielded connectors or a joke for ready-made solution to tackle HDMI emission issues?
So HDMI, always video and audio signals are really sensitive to noises because they are carrying out a lot of data and they are high-speed signals. So the most common way of solving problems here in these cables, first is to have a good shielding on the cable, and then with a good ending. And then one thing that we can see, for example, in a lot of devices are high-ending devices on the inside, is that you have this kind of gaskets. They can be cutted like this one in a really thin square, and then they can be stamped in order to have the shape of an HDMI connector. In this way, when you are connecting the HDMI to the device, you are ensuring that the whole grounding of the HDMI cable is in contact with 360 degrees of connection to the ground of the final device. So at the end, we're ensuring that the housing has a continuity through the cable. So I would say this is the most common way. There are, of course, some filters for the HDMI, but normally the first solution is to use this solution because it's much cheaper. To implement a filter will be more expensive.
Okay. So let's move to the next question. Distance, can I shield inductor? I think this means inductor. Can I shield inductor using ferrite sheet?
Sorry, can you repeat it again?
Can I shield an inductor, but here stands inductor. So
I guess it's inductor, right?
Yes, I also think that. So can I shield an inductor using ferrite sheet?
Yes, of course, it's possible, and it's quite common, I would say. We have requests like this from our field application engineers and salespeople, sales engineers, about these designs many times. So when we have inductors that are problematic, that are radiating too much noise, then we can seal them like in this way we're showing before. You can just stick some ferrite sheet on top of it, or absorber sheet, and then we are preventing this noise from coming out of the inductor. It doesn't have any interference because we still need, this inductor creates by itself a magnetic field. This is impossible to erase because it's how the inductor behaves. We need this magnetic field because if not, the inductor wouldn't behave like it does. What we can do is to place this kind of absorbers or ferrite sheets in order to prevent this noise or this magnetic field to affect other parts of our device.
Okay. So let's come to the next question. Antonio, is there a difference in performance when using the SMT clips versus using a shield soldered directly to the PCB?
Yes, sure. There is, because when we're going higher frequency, there are small slits that cannot be prevented by with the clips. If we solder the shielding cabinet, that at the end is a Faraday cage, if we solder this Faraday cage straight directly to the PCB, then we are also shielding against very high frequency. With the shielding clips, there are small slits or slots, and with very high frequency signals can become problematic. So at the end, it depends on the attenuation level that is required by the customer and by the designer when they are using it. So either they can test with the clips, or and if it doesn't work, they can use the other one. But first of all, depends of if they want to make it pluggable or not. And if not, if they don't need it pluggable, then I would recommend to use straight soldered cabinets.
Mm-hmm. Okay, so thank you for the explanation. And then let's move to the next question. Antonio, does the metallic painting efficient when we have plastic housing, or does it exist another way with plastic housing?
Normally with plastic housing, the most common ways that like you said, was Dennis. It's a good question because normally the most common thing to do is to use a metallic painting. What we need to ensure when we do this metallic painting is that on the joints, this metallic painting is not so effective. So we should be using something on the joints, like for example, the gaskets or the tapes, aluminum tapes and copper tapes. In this way, we're improving a lot the final attenuation or the shielding effect of the housing. I will say for plastic housings, there is no other way. Either use this metallic painting, or you use tapes all around it. That makes no sense, I think, from the price point of view.
Okay. So then let's move to the last question. If there are any questions open, we will answer them afterwards via email. So, Antonio, will power adapter connected to PCB emit radiation? And if so, how to prevent the emissions?
So there are two ways. I understand when you are saying the power adapter is just common power adapter externally that is connected to a device. So for example, the charger of our laptops or whatever. Of course, depending on the adapter, there always will be a noise level. It only depends if this noise level is over the limit or not. But it's impossible to have zero noise level because the power adapters, as we all know, they have AC/DC, they have DC/DC transformers, and these transformers, every time they're working, they're creating small current peaks. These small current peaks generate noise. So this is impossible to avoid. So what we can do here, the normal way is to ensure good shielding on the cable. This will be a first one. Good ending at the end, so the connection between the power adapters should have a good grounding with the final device. And if we still have some noise at the end, when we connect it to the PCB, normally a common mode choke or something like this it's used as a filter on the entry point.
Okay, so thank you, Antonio, for your explanation. And now we are finished with our webinar. If there are any questions left now, we will answer them afterwards via email.
Thank you very much for your questions.
Yeah, also from my side, thank you very much. And also for your attention. I hope you enjoyed our webinar. Also, many thanks to you, Antonio, for this great webinar.
Thanks, Marcus, for the support.
I hope you will hear us at our next webinar, and I wish you a good day. Goodbye.